A very good morning. In our previous class, we discussed about a pressure distribution in idealized plane slider bearing with fixed shoes. We derived the P equation. Okay, that is what pressure distribution. And today we are going to discuss about a load carrying capacity of same idealized plane slider bearing with a fixed shoes. Same fixed shoes. Here we are going to discuss or derive a load carrying capacity W. Okay. So load carrying capacity of this idealized plane slider bearing with fixed shoes. Okay. The area, the figure what you are seeing is it's the same plate, moving plate with a velocity of u. It's a velocity. This is a velocity. Okay, and it is in the x direction, and in the z direction no end leakage. Okay, and here it is the y direction. Capital B. B is the length of the bearing surface. Okay, and L is the width. B is the length. Okay, and this is what the pressure distribution. In the last class we derived this pressure distribution along this length of the bearing surface, and it is minimum here. Minimum means atmospheric, or we can call it as a zero. Okay, and here pressure is maximum. Okay, the area under pressure distribution, a center multiplied by a length of the bearing is equal to the external load W acting on the bearing. Means a W, if you want a load, means load carrying capacity of this, the area which is under this pressure, area of under pressure curve into into length width of the bearing surface, width of the bearing surface. Okay, that gives the load carrying capacity of entire this bearing. Okay, for that we consider a small elemental area. This is dx. Okay, instead of b we consider a dx. Okay, and this is a, we can call it as a p anywhere on this parabolic graph. Okay, you can take anywhere. If you want you can take here. Okay, here if you want you can take, or here if you want take. Okay, no problem, but I consider here. And this length is dx, and it is an at a distance of x from the h1. Okay, and p is the pressure of this. Okay, total pressure. So this P into area of this means, area means dx into the length. If you multiply dx, okay, into L, that gives the overall area into P. Okay. So this multiplied with this, it gives the load carrying capacity of this small area. If you want to whole plate, means you have to apply integration with respect to the limits 0 to b. Means this graph is moving, means varying from this point to this point. Okay, we have to consider whole plate with a limit of 0. Here this point limit we can call it as a 0, and here this point limit we call it as a b. Okay, integration of limit 0 to b, because we got only a small this small area load carrying capacity. If you want whole plate, means you have to apply integration, means adding all these small areas, which gives the whole plate load carrying capacity. Okay, for that we have to apply integration. Integration means adding all these small elements from 0 to b. And what about this w is equal to, we can write the equation w is equal to 0 to b p dx into L. So this load is a capacity of bearing from given conditions. Okay, this load is a capacity of bearing for a given condition, that is for given a minimum distance h2 under a operating conditions and the relating inclinations angle between the surface. The velocity of the oil and the velocity of the slider also are the other parameters which consider for given operating conditions. Okay, which are the parameters we are going to consider? Here we are considering the h2 is the minimum, okay, and the velocity we are going to consider, viscosity is also we are going to consider, and this is the what equation we are using for find out the load carrying capacity of this fixed shoes. W is equal to integration 0 to b p dx into L. Okay, let us call it as this as equation 1. This equation you also get in the data handbook. Data handbook. Okay, you can copy from the data handbook. See here. Okay, this is what the equation got from the figure. And here L is a constant, that's why I take it outside. So L into 0 to B, L into 0 to B, just a minute. Hello. So this is what the equation W is equal to L is constant, that's why I take it outside, and this P into dx b to b. Okay, so now we can call it as equation 1. So we know that already from the previous equation, x1 is equal to x by b. Okay, we designated these terms. Okay, so I want x value means, so x is equal to x1 into b. So dx, if we differentiate dx, it is equal to dx1 into b. So wherever the dx is there, okay, we just replace this dx by dx1 b. That is what I written. So dx, which is equal to b dx1. And now we have to, at the same time, we have to replace these limits 0 to b by with respect to the these 0 to b with respect to x. But I want in terms of x1 means, again we have to use where x is here. Take this one same, okay, where x is 0, first limit x is 0. What about x1? That we have to find out. So x1 is equal to 0 by b. So anything divided by b mean 0 anything divided by anything means it is 0. 0 anything means 0. Okay. So x is 0, x1 is also 0. When second limit is x is equal to b, then what about x1? So x1, x by b, so just place the value of x means b by b, so get cancelled, is equal to 1. So x is equal to b means x1 is equal to 1. So these limits we have to replace. Okay, when x is equal to 0, x1 is also 0. When x is equal to b, x1 is equal to 1. So now substitute all these values, okay, in the above equation 1, it is become w is equal to 0, that is what, 0 to 1. Instead of b, I written 1. So p l b dx 1. Okay, so now these two are the constants. Okay, take outside. So w is equal to lb integration 0 to 1 p into dx 1. That we can call it as a equation 2. So introducing the value of P, we already got the value of P in the last derivation. That is what pressure distribution P value, we already got that. And that P value already in terms of X1, alpha and A, these are the parameters which contributing to the load carrying capacity, because alpha is the inclination angle. If you change that inclination angle, it will change the load carrying capacity. It will change the pressure, the pressure change the load carrying capacity. So all these terms are interconnected. So we just replace this P value in the equation 2. Okay, just directly copy from the data handbook, no problem. So in the data handbook, these equations are available. Okay, the P equation is available from the data handbook. Okay, so LB 0 to 1, and here in the place of P, I write the value of P and the x1 as it is. So now take the some common terms outside. Okay, reduce that form to 0 to integration 0 to 1, 0 to 1 x1 into 1 x1, because x1 is the integratable term. In this only x1 is the integratable term and others are constant. That's why I took outside. So now this is the integratable form, and here same thing, the x1. Okay, I just multiplied this x1 into inside the bracket, so x1 into x1 whole square. That we can call it as a equation 4. So now the quantity of this term we can replace by or rearranged by. Okay, this term is either rearranged or replaced by this term. Okay, this term is you can copy from the data handbook. It is available. Okay, or else I just make the these terms I expanded. Okay, and I introduce the one term. Okay, by simplifying we'll get this term. So this term which is equal to this above term. Okay, wherever this term is there, you just replace this term by this equation 5. Okay, so in equation 4 replace this term by equation 5, then the equation 4 will become same w, same this constant term. Okay, in the place of this I return this, because for easy to integrate. So now I introduce this term, and next what I did is I just multiplied this term, this dx into inside. So okay, this whole term is positive and this is negative. So negative 1 by alpha square dx1. Okay, now it is integratable form. We can apply the integration easily. That's why I reduced equation 4 to this. Equation 4 is we cannot apply the integration easily. Okay, there are more x1 terms. So next, the same w which is equal to same constant terms, and here 1 by alpha square is there, that we integrate, that is x1 minus x1, that is the integration of dx 1 is equal to integration of dx is equal to dx1. Okay, and apply the limit 0 to 1. That is what I did here, and this term I written same as it is integration, and these are the constant terms. I just take the some constant terms and simplify. Okay, these get cancels. Okay, alpha is also get cancels, and here 0 to 1. So if 0 means everything is 0 and 1 means minus 1. So minus 6 mu view alpha. So here alpha square is there. Okay, 1 alpha get cancelled. Okay, 1 0 minus 1, and here same thing, and this is alpha x1 plus a minus alpha square by 2a minus alpha, and this term. So now adding and subtracting the numerator. So adding and subtracting to the numerator, and we can reduce this term to this term. Here I am going to add one more term. Okay, so one more term I am going to add here, that is a minus alpha. Okay, I am going to add plus as well as minus. For these two terms I am going to reduce. So W is equal to same thing, and here reduced form. Okay. So next, the numerator is a differential coefficient of that equation. So integration is log of the numerator. Okay. So by taking the by applying the integration, this is already we did the integration. Only this term you have to do the integration for this. Okay, it is just like a 1 by x. The integration of 1 by x, which is log x. Okay, same thing we used here. So 1 by these terms we take common outside. Okay, and here minus alpha for this, again integration log, and again for this term again we did integration. So it is 1 by minus 1 by 2 alpha. Same thing for this side also. Okay, a this is a constant. Okay, we simplify and take this outside. So 0 to 1, these are the limits. After applying these limits to inside the bracket and simplify, the final load carrying capacity of this equation will become, and here also we take the common outside 6 mu by alpha or alpha square, we take the common and simplify. The final equation will become, and W is equal to 6 mu ul 1 by alpha square whole bracket ln a minus alpha by a plus 2a by 2a minus alpha. Okay, this equation you can get it in data handbook. Here it is very simple. Okay, just rearranging and applying the integration will get the load carrying capacity of the plane slider bearing with fixed issues. So next, one more equation is that is for the center. In a hydrodynamic plane slider bearing, this uh, load carrying capacity of the equation is depends on L and B. Okay, it depends on the L and B, the velocity moving plate U, the viscosity of the fluid mu, and the angle of inclination alpha. This all depends on the quantity of A. So the load bearing maybe we can take it as the quantity which mu u by Pb. It's a dimensionless component. The load carrying capacity increases with decrease in the quantity of A. For the given dimensions, these may be taken as important parameters like alpha, inclination, and A, and L, mu, and U. These parameters which contributes for the load carrying capacity of the bearing. And one more next equation is the location of center of pressure. Here this is what the pressure distribution. We know that pressure distribution is parabolic, and here where the pressure is location of center of pressure, that is what we have to locate. Okay, for that same H2 H1 P. Okay, and W is the load, and X, the W is in the A distance, and P is in distance of X, and B is the length, L is the width. For that, we consider one equation to find out that external external moment about the point O, that gives the external moment is equal to A into W. Okay. So if you want moment means here it is a one of fixed, and here I am going to apply the force. I want moment at this point A and B. Okay, I want moment at this point A means this is a length. So moment at A is equal to F into L. Okay, the same thing I am here considering. So external moment at this is a what external moment at 0 A W, that is what the point A at a moment. The moment due to the pressure force, which is equal to integration 0 to B P L dx dx. Okay, this is what the force. Here I replace this x1 in the place of x. Same thing what I did in the previous. I replace these terms, and now the equation will become integration 0 to 1 PLB x1 dx into B. That we simplify, and we know already the value of P, pressure distribution, from the data handbook. You just take this, okay, and substitute here. So here the moment at A, which is equal to plus equal. And integration we already know that it is 0 to 1, that is already we did in the previous load carrying capacity. Same thing we have to use here, 0 to 1, same thing. And upon integration, you people already know that, or better idea having integration how to do. Upon integration of above equation, okay, if you do the integration and apply the limit, the entire equation will become this. Okay, here we take this b and send to the left side. So a by b, which is equal to the a by b, which is equal to center of pressure. A by b, it's a ratio which is equal to this term. And this term is available in that hand. Okay. Next, frictional force in the plane slider bearing and coefficient of friction. For this, there is no derivations. You just use the equation. These equations are available in data handbook. So frictional force F naught is equal to, this is the equation, and coefficient of friction small f is equal to F naught by load, and this is what the final equation. Okay, there is no derivation for these terms, for the center, for the frictional force, for the coefficient of friction. Only you will get pressure distribution or a load carrying capacity. So in the next class, based on these equations, frictional force, coefficient of friction, as well as pressure distribution or center, by using these, we solve some numerical problems. So if you solve those numerical problems, it will complete your half of the fourth module, first chapter. In the next class, after completion of numericals, we'll move on to the pivoted bearings, which is similar to the fixed bearings. Okay.